Okay, let's start. First, I want to talk a little bit about the homework. The homework is number 4. Number 4B. What's the number question for number 4? Part. Which part in number 4? The first question. First. B and E. Okay. For example, B. Okay. B is A and E equals 1 over N. Let's look at what's the question. Oh no, this one. This is number 3. 4. B is N squared over 2 over N. Now, number 4 asks us to prove the sequence AN with AN as given are monotone or eventually monotone, right? Now prove it. How to prove it? Whenever you're asked to prove something with some term, when this is our first time to study this part, you should use the definition. Okay. But last time I said you can also use the equivalent statements. Equivalent statement is what I said in my slides, lecture notes I wrote. For example, what means equivalent statement for increasing? AN increasing. This is equivalent to say AN plus 1 minus AN greater than 0, right? Or equivalent to say AN plus 1 over AN greater than or equal to 1 increasing. Yes. Or which one? Or AN plus 1 greater than or equal to AN. Right? These 4 statements are equivalent. Means if you want to prove AN is to be increasing, you can prove this one or prove this one. And now for this sequence, you can I couldn't say increasing or decreasing. Okay, it should be decreasing. Okay. Now if you are going to prove that it's decreasing, use the equivalent. Right? This means increasing. Increasing means that the later one is greater than the previous one, right? Decreasing means the later one should be less than, right? Or this one less than equal 1, right? So for example, proof, you can do this way. Proof AN plus 1 over AN. If you can prove that this one is less than or equal to 1, then you, based on the equivalent statement, so it's decreasing. Okay, so this is proof. Why I use the quotient, I didn't use the difference, because this is the quotient form, right? When we use quotient, it's easy to cancel something, right? Or when this expression is a product, we can always use the quotient, because product means that we have factors, so we can cancel it, right? So in this case, this is equal to n plus 1 squared over 2n plus 1 over n squared over 2n. Now this can be cancelled a lot. Let me see. Anyway, the first part is the same thing. N plus 1. Let's keep it. Okay. N squared. Then this one divided by 1/2. This 2n cancel this 2n. Then we have 1 over 2. Here we need to be careful. Let me see. When n is 1, look. When if n is 1, then this 2 squared over 1 squared times 1 over 2. This equals 2. This is not less than 1, right? But we can see that, since I believe everybody can see the limit, right? The limit for this expression should be 1, right? Then times 1/2 means the limit will be 1/2. Limit will be 1/2 means this expression should be eventually less than or equal to 1, right? Eventually. But since the first one, we can say, now this one goes to 1/2. So AN plus 1 over AN is eventually less than 1. Right? But A2 over A1, this equals, for example, 2, n is 2, right? N is 2. Well, S2 is 2 squared over 2 2 square over 1. 1 is 1 square over 2, 1. Simplify, okay, that's equal to 2, right? That's greater than 1. Therefore, the sequence is not strictly decreasing, but eventually decreasing, and eventually strictly decreasing. Right? Eventually strictly decreasing. So, AN is eventually strictly decreasing. Okay. The question asks us to prove the sequence. Okay, eventually. So this is the proof. Okay, just use this equivalent statements. Okay. For other parts, you can do it similarly. Okay. So I'm not going to talk about that. Then next is number 5. To prove that for an eventually decreasing sequence AN, there are 2 possibilities. Okay. For example, AN is bounded below. AN is bounded below by M. Then there exists L such that limit n goes to infinity, AN equals L. Now, means we have this condition. This is what we are going to prove. Right? But don't forget the original condition. Right? AN is an eventually decreasing sequence. Right? So AN is eventually decreasing. Okay. That means we need to, based on these 2 conditions, and show that there exists L such that limit AN equals. This condition just means we want to show that AN converges. Right? Converges. Converges just means there exists L such that this limit, right? Okay. For every statement, try to use the definition proved. In order to prove this one, we need to find for any, what means this? Right? There exists L sum. This limit of the L means for any epsilon greater than 0, we want to find, right? There exists the definition, there exists n star such that AN minus L less than epsilon for all n greater than n star. Now, such an n star is what we are going to find, right? For any epsilon greater than 0, you can always write for any greater than epsilon. Then you need to find such an n star, such that this is really less than this epsilon whenever n greater than this epsilon. Okay? Now, we do this way. First, based on the bounded below by n. Right? We have 2 conditions, right? This is the first condition, the second condition. From the first condition, I simply write 1. Okay? We know AN has a bounded below, means we have lower bound. Lower bound means we have a infimum. The infimum. Say L. Say L. Later on, we'll show that this L just means this limit. Okay, L. And remember this, we introduced this part in section 1.7 a long time ago. Okay, what is bounded? Bounded, right? For any bounded set, we have supermom. If it's bounded above, we have a supermom. If it's bounded below, we have an infimum. Right? Supermom means the smallest upbound infimum means greatest low bound. Okay. Now, based on definition, the definition of infimum for any epsilon greater than 0, there exists a n0, okay, ak, whatever, okay. The a n0 such that a n0 minus L less than epsilon greater than 0. Greater than 0 is obvious, okay, because this is increasing sigma. Is it decreasing? Wait a minute. Decreasing. So we have infimum. Decreasing, yes. Decreasing. So the L should be smallest, yes. So this just means 0 less than a and 0 minus m. Right? Because it's decreasing. Decreasing means this is a lower boundary. Now this lower boundary means every number is greater than this, just greater than 0. Less than epsilon because this is less than epsilon, right? So this is true. Okay. Now next we need to use the eventually decreasing. Okay. From 2. What means eventually decreasing? Check the definition. Means there exists a stop such that a n decreasing less than a n for all m greater than n and n greater than n star. This means eventually decreasing. If it's decreasing means what? If it's decreasing means for all n greater than n, an less than an, right? That's the decreasing definition. When n is bigger, n is smaller, right? But now it's eventually decreasing. Means there exists n star. When n big enough means greater than this n star. This is true. Now choose. We can put this n1 star. Okay, n1 star. Choose n star to be maximum of here n0 and this n1 star. N1 star. Okay. Choose this one means what? Let me see. I just choose it. Okay. Then first, then a n minus L choose that then for all n greater than n star. Greater than n star. This greater than 0, definitely, because right, this is a lower bound. Less than a n 0 minus L, and this one less than epsilon. This inequality is true. Why is this inequality is true? From here to here. Why is this true? Because it's eventually, this is true. This is true. Now, for n greater than n star, should I do this and this greater than n star? Let me see. I should say let me, here should be larger than maximum. For any epsilon greater than 0, why this is true? I need to do this one less than this one. If this one less than this one, means is there anything not very strict? Not strict. Superman means this is true. But this is always true. Why an must be greater than n must be less than n0? This is true. Then n0 must be greater than this n star. Right? Greater than the n star. But it may not be greater than n star. There's a little problem here. Okay? Let me leave it here. Let me simply open up the class. Okay? Now this is a rough idea. Okay? You two use the ideas almost the same. Okay? So this just means what? This just means absolute value because this is positive. So this just means a n minus l less than epsilon. Right? Whenever n greater than n star, something like that. So this just means limit a n equal to l. So this is proof. Anyway, the idea is use the bounded below, we can find one element. Now for any given epsilon, we have find one element, a and 0, such that this difference less than epsilon, greater than 0. This is based on the supermon, intimum. Okay. Second, use the so-called decreasing. We can derive that for all mn or n greater than some n star. Then this is always true. This is always true. So based on definition of limit, so this is true. Okay, this is the idea. So anyway, we need to use the definition. And there's a little problem here. Let me think it over after class. Okay. So this is the question for number 5. For number 6 or number 7, is most of you did perfectly almost. Okay. So you make a point. Okay. Today, last time I introduced Cauchy sequence. Right? You remember Cauchy sequence definition? Before we introduce the Cauchy sequence, we also introduced the accumulation point, right? And Bolzano-Weierstrass theorem. Bolzano-Weierstrass theorem says every bounded integer set of real numbers has at least one accumulation point. Now, what's Cauchy sequence? Okay, let me review for you Cauchy sequence. AN is called the projector. I don't know how to use it. It doesn't work. It's called Cauchy sequence. If for any epsilon greater than 0, there exists n star such that an minus an less than epsilon for all n greater than n star. This is the definition of Cauchy sequence. Now today I'll show you first examples to see whether a sequence is Cauchy or not. Okay. Example 1. an equals n plus 1 is not Cauchy. Okay. It's not a Cauchy sequence. If we want to show that it's not a Cauchy sequence, means there exists some specific, a particular epsilon 0, such that this one greater than the number. Always true for some element, right? Proof. Note that if m, let me say 4, okay, for m not equal to n, and m greater than n, just greater than, okay, we have an minus an, the absolute value just equal to m plus 1 minus n plus 1. This just equal to m minus n. Right. When m is greater than, right? This is greater than equal to 1. Right? As long as m not equal to n, the difference is greater than or equal to 1. Therefore, I'm going to show that this is not Cauchy. Not Cauchy, I mean, I want to show this condition is not true. Okay. Therefore, if we pick epsilon 0 equal to 1/2, then am minus an will be greater than epsilon 0 for all n not equal to n. So am is not a Cauchy. Why? After I get this one, then I claim this is not Cauchy. Why?
Because a minus a is going to be equal to 1 or more.
Equal to what?
1 or more. Because like it's.
I claim it's not Cauchy. So this is the definition for Cauchy sequence, right? If I claim that this is not Cauchy, that means what I obtained violates this definition. The definition says for any epsilon greater than 0, the difference of an and an to the absolute value will be less than epsilon for all n greater than n star. Right? Here, I found a U required for any epsilon. This is true, right? Now I found for a specific epsilon 0. This one means this is not true. Greater than means this is not true, right? For this epsilon 0. No matter what n star you pick, no matter n how big they are, as long as n is not equal to n, this is always true, means this cannot be true. Therefore, what I obtained violates the definition. Right? Here you say there exists n star, right? Then when n greater than n star, this is true. But whenever n greater than n, as long as they are not equal, this will be greater than this epsilon 0 for this specific one. So this violates. So it's not a Cauchy. Okay. Cauchy. Second example is this is not. Now this time I will show is. Okay, is. very, very basic example. Prove that AN is Gaussian. Okay, Gaussian. This Gaussian means we want to show that definition. Okay. Show that is a Cauchy sequence. Just like we prove the convergence of a sequence, let's analyze it. Okay. Based on definition, we want to show that for any analysis, for any epsilon greater than 0, we want to show that this is what I learned from you. Dr. Truens with this. Want to show AN minus AN, this one less than epsilon for all n greater than n star. Of course, there is n star. No, there is star should be after 1 to show. There is n star. Okay. Now let's see what's n. N is 1 over n. N is 1 over n. Right? We want to show that this one less than epsilon. Equivalent. Equivalent. Now this one is equivalent to m, here's m minus n. Right? Because we don't know m and n, which one is bigger, which one is greater. Why? We are going to find such an n star, right? N star. Easy, huh? But this one, I claim this one. I claim. Can you see? Note that this one, m minus minus n without loss of generality. We usually use this word, right? Without loss of generality. Well, Mn, there must be one number bigger, another number smaller, right? Now Mn, which one is bigger? Because there's an absolute value here. This is a trouble to us. So I want to remove this absolute value. So I assume one number is bigger, okay? Mn, no matter which one is bigger, okay? For example, without loss of generality, assume m greater than n. M greater than n. Then this equal to then m minus n absolute value over mn. This equals m minus n over mn. Now m greater than n, this is less than 1 over n. Right? Can you see it? This is less than 1. Right? So by the red mark, this is less than 1. Right? And the m greater than is positive, so this is less than 1 over n. Right? Now, if you may say you assume m greater than n. What if n greater than n? Right? If n greater than n, now this m minus n absolute value over m, this will be less than n minus n over n times 1 over n. But equal, it's equal, right? Then this is less than 1 over n. Right? If n is greater than m, then absolute value of m minus n just equal to n minus n. And this is less than 1. Right? Or less than 1. So this is less than 1 over n. Therefore, we can see that this is less than both, either one. Right? Less than either one. So we can say this way. Then means what? In whichever case we have this one, in this one minus n over m n should less than maximum 1 over m and 1 over n. Either less than this one or less than this one. So it must be less than the bigger one, right? Maximum. Okay, now we can prove. Now we want to show that for any epsilon greater than 0, we want to show that there is n star such that this is true. This is true, right? Now if this is true, means this is true. Now we see that this one, the left hand side, always less than this one. If we let this one less than epsilon, right, we let this one less than epsilon, then this one will be less than epsilon, then this one will be less than epsilon, then this less than epsilon, then this definition is a quotient. So we just need to find an n star such that this is true. Right? This is true. This is easy, right? We just, for any epsilon, if, for example, if 1 over n less than epsilon, means n should be greater than 1 over epsilon. If 1 over m less than epsilon, means m greater than 1 over epsilon. Now, we take n star to be an integer greater than this number. Then whenever mn greater than this one, this is always true. Greater than this one. Okay. Now proof. This is analysis proof. For any epsilon greater than 0, pick n star in n such that n star greater than 1 over epsilon. Okay. Then, whenever n greater than n star, we have n greater than 1 over epsilon and n greater than 1 over epsilon. Right? I pick n star such that for any given epsilon, I pick n star such that n star greater than this one. Now, when n greater than n star greater than this one, of course, this is true. Right? The two are true. Now, equivalently, epsilon less than 1 over n. And epsilon less than 1 over n. I like a lot, okay. So, m minus n over mn, this one less than, this one always less than this one, less than maximum 1 over m, 1 over n, then less than or equal to epsilon. This one less than or equal to epsilon because here, wait a minute, why is greater than? Epsilon greater than. Namely, 1 over n and 1 over n less than epsilon. Whenever m n greater than epsilon. This is whenever m n greater than epsilon. For each step, okay, for any m n greater than epsilon. It's right here. No, it's true. Here is also for whenever m n greater than epsilon. Now this just means an minus an. That's an epsilon. Variable and so okay. So an is cosine. Anyways, still always focus on the definition. Cauchy sequence, from now on, Cauchy sequence is almost the most important definition. Just like the convergence concept. It's very important analysis. I want to show one more example to see. In this case, an is equal to n plus 1. It's not close. This is also not cosine. Of course, just introduce definition. Now, similarly, to show that this one is not Cauchy, we want to find a small number such that an minus an will be greater than that number. As long as an is not equal to a, okay, greater than. Now, let's see. No matter how big m and n are, okay, we can always find such an m and n, they are not equal, but the difference is greater than that number. Now you see, what's this sequence? This sequence just means negative 1, 1, negative 1, 1, right? Negative 1, 1, and so on, right? So every neighbor one, successive two, okay, pair, their difference, absolute value, will be equal to 2. So, in order to show that this sequence is not Cauchy, you can just pick the epsilon 0 less than 2. Then it will be okay. Take epsilon less than 2. Now, let me show you the proof. Because if epsilon 0 equal to, for example, equal to less than 2, for example, 1, right? 1 less than 2, right? It must be positive number, epsilon 0. Then, no matter how big, no matter how big m and n are, right? I can always find an even number and an odd number. They are successive, such that one is negative 1, the other one is 1, right? Then their difference will be 2, will be greater than this case. This is the proof. Okay. So now let's see proof. Okay. Not Cauchy. Know that an plus 1 minus an, this absolute value always equal to 2 for all n equal. So if we pick epsilon 0 equal to 1, okay, no matter what n star is, we can always find n greater than n star. For example, n equal to n star plus 2, n equal to n star plus 1, right? No matter how big n star is, I pick n to be n star plus 1, n to be n star plus 2. Obviously, they are greater than n star, right? How to find m greater than some, such that am minus an equals to 2, right? That is greater than epsilon 0. this violates the definition of Cauchy sequence. So AN is not Cauchy sequence. Actually, I have the fourth example to show that this one. This one is also Cauchy. Now, the only difference between this sequence and the previous one is 1/n, right? Difference this one is. Now, here AN minus AM equal to -1 and 1/n minus -1 and 1/n, right? When you show that this one is less than some epsilon, right? Less than some epsilon. For any given epsilon, there exists n star such that this one is true whenever. Since they may have different sign, now here they may have different sign, right? If these two terms have different sign, then after subtract, the result becomes the sum, right? Because n, right? Minus minus becomes plus, right? So this one should be at most 1/n plus 1/n, right? Maybe it becomes n, right? So in order to show that this one is less than epsilon, in order to show this one, but this one is less than this one, then enlarge what is this one. If we can prove that this bigger one, if for this bigger one, now this is bigger than this one, right? If the bigger one is less than epsilon, then original of course less than epsilon, right? Now, how can we show this one less than epsilon whenever n greater than n star? No. This one should be once again, let's enlarge it. Okay, this one is less than or equal to 1/2, less than 2 twice, right? Twice of 1 minimum of. Okay. This one is less than or equal to 1 minimum of n plus 1 minimum of n. Now this time I don't want to use the word without loss of generality, right? To assume n is bigger or m is bigger. Anyone, right? Pick the smaller one. So this one should be less than this one or equal. This one also less than or equal to this one, right? Because for a fraction, the quotient form, the smaller the denominator is, the bigger the whole thing is, right? So this is true. Therefore, this just means 2 minimum and n, right? So if I choose, well, in order to show that, now this is bigger than this one. In order to show this one less than epsilon, I only need to show this one less than epsilon. Okay. If this is true, then this is true, then this is true. How to show that this one is less than epsilon? We just take this one for example as n star. Right? This is just like 2/n star less than epsilon. So we just pick n star greater than 2/epsilon. Then you can write the proof. Right? For any epsilon greater than 0, pick n star such that n star greater than 2/epsilon. Then this is true, this is true, this is true, so this is true. So it's a Cauchy sequence. Can you see the law? Is it all? Can you understand it? Nico? Alan? Almost right. Something like that. Okay, I don't want to take too much time at this concept. I want to move forward. So this is the idea. If you are good at the proof for convergence, then here is similar. But the only difference is here we have two index m and n, right? M and n. So usually we need to pick the smaller one, such that the smaller one greater than n star. Usually, okay. That theorem is